In section 11.6, we're going to be working with the areas of regular polygons. So really the last thing we're going to be finding the area of, and one of the most important here. First of all, remember that a regular polygon has all congruent sides and angles. And whenever we picture a regular polygon, we're going to be talking about multiple parts in them. Always picture a regular polygon like this regular hexagon inscribed in a circle. So I have this like reddish-orange circle going around. It's inscribed in the circle because every vertex touches that circle. Now the reason it's important to picture them inscribed in a circle is because we talk about the center and the radius of that polygon. It's the same as the center and the radius of the circle that it's inscribed in. So if I want to talk about the center of that hexagon, it's the same as the center of that circle going around that hexagon. And if I talk about a radius of the hexagon, it's the same as the radius of that circle. So it goes from the center to a vertex of the hexagon, which would be a point on that circle. So there we have a radius. And then this other really important part that we talk about is called the apothem, or the apothem. You can call it by either way there, apothem or apothem. Now that's the distance from the center to a side at a right angle, at a perpendicular, right? That's our symbol for perpendicular. So an apothem goes from this center to a side at a right angle on a perpendicular. There's an apothem. This is an important part that we're going to talk about here. And another thing that we're going to talk about relative to the circle is a central angle of a regular polygon. Remember, a central angle has to have its vertex at the center of a circle. In this case, a central angle is formed by two consecutive radii in this hexagon, and I want to be able to find its measure. So if you think about it, like how many radii could you draw in this hexagon? Well, I could draw a radius to every single vertex. So in this case, I can draw 6 radii, which means how many central angle measures do I have? I got 1 central angle here, 2, 3, 4, 5, and 6. Now I have 6 central angles. Well, wait, what do I know all the angles in a circle should add up to? They should add up to 360, right? So in this case, I take 360 degrees, I divide by the fact that we have 6 central angles. Each one is 60 degrees. However, in general, I'm not always going to have 6 triangles, right? I'm going to take, or 6 central angles, or 6 triangles. I would divide by, I ended up dividing by 6 here because it's a hexagon. It had 6 sides, 6 triangles, but in general, I divide by n. Now remember, n stands for the number of sides. If it was an octagon, I would do 360 divided by 8. Okay, I do 360 divided by 6 in this case because it was a hexagon. But in general, if you need a central angle, there's going to be the same number of triangles as there are number of sides, and so the central angles is going to, again, be the same as the number of sides. Do 360 divided by n. So first example, looking at the parts here, I have regular octagon A, B, C, D, E, F, G, H is inscribed in circle X. Regular octagon has 8 sides. Inscribed in circle X, X is the center. Oh, identify the center. The center is X. Center of that circle and that polygon, that octagon. Identify a radius. A radius goes from the center to a vertex. Here I have 2 drawn. X to A is a vertex, and X to H. So line segment XA is a radius, line segment XH is a radius. Identify an apothem, an apothem. Remember that goes from the from the center to a side at a right angle. That would be this blue segment here, which is XZ. Okay, at a perpendicular to a side. And finally, identify a central angle of the polygon. What angle is a central angle? It has to be vertex at the center, so I know X is going to be the middle letter. A central angle is formed by 2 radii, so I'm going from A to X to H. This entire thing there is a central angle then. Angle AXH. Remember that a central angle does have to go between 2 radii. Okay. Oh, and first example is find the measure of that angle AXH, that central angle, which again is the entire thing. Now I know that if I drew every single radii here, I would have 8 triangles, 8 central angles because there are 8 sides. And all of those central angles should add up to 360. So I'm doing 360 and dividing by the 8 central angles that I have. And I find out that each of these is 45 degrees. So that central angle, that whole thing, is 45 degrees. Well, then what about here, angle AXZ? AXZ. So that's only this portion right in there. Well, if this is an altitude of an isosceles triangle, I know it's isosceles because these radii have to be congruent, then this also is a angle bisector. So the fact that it's at a right angle, it's also an angle bisector. I've cut this 45 degree angle in half, so I divide by 2. And we have a 22.5 degree angle there at angle AXZ. And one more question here. What's angle ZHX? ZHX. So that's this angle here. Oh, well, remember how these are 22.5, right? This one is as well. This is a 90 degrees. So now I have a triangle with a 90 degree angle and a 22.5 degree angle. So I'm really taking the angles in a triangle I know add up to 180. So I'm subtracting the 90 and I'm really only left with 90. Minus that 22.5 degree angle right here. Okay, 90 and 22.5 being subtracted from 180. And that would have to be 67.5 degrees. So just knowing it's a regular polygon, you can find central angles. You can use that apothem, divide it into 2 right triangles, and find all the angle measures within those triangles, which is kind of neat. All right, discovery. What is the formula for the area of a regular polygon then? We're going to figure that out. And the first thing we have to do is draw all the radii. So actually here I have a pentagon, okay? But I'm going to generalize and say it could be any regular polygon, okay? But I'm going to draw all the radii here. Let's see, maybe I'll change the color. And how many radii am I going to be able to draw? Well, it's a pentagon, so in this case, 5. But if it was a hexagon, I could draw 6. And if it was an octagon, I could draw 8, etc. Okay. Well, I did that. I drew all the radii. This breaks the polygon into what shapes? Well, it breaks it into a bunch of triangles. So what is the area of this pentagon? Well, I guess I know the area of a triangle, right? Area of a triangle is 1/2 base times height. How many triangles do I have? I have 5 triangles. So I have 5 1/2 base times height, right? The area of a triangle is 1/2 base times height. Question is, what are the base and the height of the triangles relative to the actual polygon? Now you notice I labeled a few things. The apothem I labeled as A. And that goes from that center to the side at a right angle. Now S I labeled for the side length, and if this is a regular pentagon, all of these would have length S. The side length would be the same. Oh, remember that N stands for number of sides. So in this case, yes, I know I had 5 triangles. But do I always have 5 triangles? Well, if it was a hexagon, remember how I had 6 triangles? And if it was an octagon, if I drew every single radius, I would have 8 triangles. The number of triangles is the same as the number of sides, which we know we call N. And actually here I'm going to erase 5. Instead of 5, it would just be however many triangles would be the number of sides. Now I need the base and the height of each of these triangles. For each triangle, the base is the side length, which I'm calling S. And the height is from the top vertex at a right angle to the side, which is our apothem. So this is the formula for any regular polygon. Each triangle would be 1/2 S times A, base times height. And there'd be as many triangles as there are sides. I'm just going to write it in a better way. These are all being multiplied. I can do any order, right? So 1/2, I like doing ANS because it's like the abbreviation for answer. 1/2 ANS, apothem, number of sides, side length. Maybe you want to change the order of that. Maybe you like 1/2 NSA. Maybe you'll remember NSA better. Or 1/2 SAN, SAN. 1/2 NAS, NAS. It's kind of up to you, but we've discovered the formula for area of any regular polygon is 1/2 ANS, 1/2 NSA, 1/2 SAN, however you want to do those letters, whatever order. But it's 1/2 times the apothem times the side length times the number of sides, and this will work for any regular polygon. Let's do an example here. You're tiling a floor with regular hexagons with a side length of 8 inches. What's the area of each tile? You notice all I'm given here is that it's a regular hexagon and I'm given side length, and that's actually all I need. Let me get a hexagon here. Hexagon is 6 sides, remember? Regular hexagon, side length 8 inches, so all I know is that this is 8 inches right here. And I'm hoping that that's enough, and it is, because a hexagon has some cool properties here. I'll just make this larger. Now here's what you're always going to need to do. The fact that we have this formula 1/2 ANS, we're going to always need to draw in these triangles, because with area being 1/2 apothem, I need to draw in an apothem. N being number of sides, well, I guess I know it's a hexagon, it's 6 sides, and S being side length, I've got that. Looks like the only thing I need is apothem here. 1/2, I don't know the apothem, I'll leave it blank, but I do know the number of sides, it's a hexagon, so 6. I do know the side length, they told me side length is 8 inches. Okay, here's where some work comes in. How am I going to find the apothem? We'll identify the center and draw in an apothem, which goes at a right angle to the side. How am I going to find this? Continue with the triangle, draw in a radius, and probably another radius here. Now what you want to do is find that central angle. To find a central angle, there would be 6 triangles in that hexagon. A hexagon is kind of the coolest one because you take 360, the angles, sum here, divide by the 6 angles there would be, and a central angle of a hexagon is 60 degrees. But, seeing that we drew that apothem, we have these right triangles of 30 degrees each. We're going to deal with that a little bit tomorrow. I guess with the 60 degrees, we actually have a lot of firepower here. The fact that this is a 60-degree angle and the radii are obviously congruent, these 2 base angles are also congruent because of the isosceles triangle. These angles are also 60 degrees. A hexagon is made up of 6 equilateral triangles, equiangular, equilateral, and you know that if you have 60 degrees for all the angles, you have all sides congruent, meaning 8 inches is not only the side length of a hexagon, 8 inches is also the radius of that hexagon, which is kind of neat. And this radius would also be 8 inches, obviously. Now, I still need to find that apothem, but here's the cool thing. Again, apothem splits that side. It's also a perpendicular bisector or a median, so if this whole side was 8 inches, this portion is 4. Now I have a right triangle, and I can find that apothem, which is my missing leg. I have a leg of 4, hypotenuse of 8 inches being the radius. So I'm going to do hypotenuse squared, which is 8 squared, minus the 1 leg I know, which is 4 squared, and that would equal the apothem, or that other leg squared. Now, 8 squared minus 4 squared, 64 minus 16, is 48. And that equals the apothem squared, but undo squared by taking square root. As a decimal, the apothem is 6.93. I'm going to keep this answer in my calculator, so instead of doing 6.93, I'm leaving what I have, the longer decimal, in my calculator, and now I can find the area of that hexagon. Notice I just put in my apothem here. So area of the hexagon is 1/2 ANS. Apothem we found was 6.93. Using the fact that a hexagon is equilateral triangles and Pythagorean theorem, we found that apothem. Number of sides, 6 sides. And S was side length, which they told me was 8 inches. Again, I'm using this exact answer I had in my calculator. 1/2 times that apothem times the number of sides times the side length. And I get 166.28. Side length was in inches, area would be inches squared. And there you have it. The first time you found the area of a regular polygon here. Let's try this formula one more time. Here I have a regular pentagon. Oh, find perimeter and area. Perimeter should be simple, although we don't have the side length, do we? That's something that I'm missing. So let's try to figure out this side length first. Can't find perimeter yet. Well, I guess I'm not even going to be able to find the side length first. I have this right triangle. Now, 8 is my radius, right? 6.5 is my apothem, my apothem. I'll have to find this portion, this leg of the right triangle, then the side length, S, will be double that, right? Because remember how if I had the second radius drawn here, this side would have been split. So let's find this x. Now I'm doing Pythagorean theorem. Hypotenuse squared, 8 squared, sorry, minus the one leg, 6.5 squared, would equal x squared. 8 squared minus 6.5 squared. I'm looking at 21.75 equals x squared. And of course undo squared by taking square root. Now that portion, that x is 4.66, about. But really I want the side length, so I'm going to take this times 2. Because remember how this portion, the side is actually double, the side is actually double that. Okay, because of the fact that it's an isosceles triangle, that altitude is also a median or a perpendicular bisector. So I'm keeping that answer in my calculator and just multiplying by 2. And actually keeping that decimal, I now get 9.33, which you wouldn't get if you used the rounded answer. But there's my side length. Now I can finally find my perimeter. Perimeter would be the side length of 9.33 times 5, right? Because it's a pentagon, there's 5 of those. I'm just keeping that decimal in my calculator again. Perimeter is 46.64. I'm not given units, so just units, perimeter is a distance. And most importantly, let's find the area of this regular polygon. My area formula for a regular polygon is 1/2 ANS, or NAS, or NSA, however you're going to remember that. 1/2 times, do we know the apothem? Center to side at a right angle is 6.5. Do we know N, the number of sides? Pentagon, so 5 sides. And do we know S, the side length? Oh yeah, the side length was 9.33. Approximately there. I'm actually going to use that exact answer I had from before. I'm going to do my half times my 6.5 times my 5 sides and times my side length. And it looks like my area is 151.57. And no units given, but units squared because we're talking about area. So today, looking at how we developed that area formula for a regular polygon, and some examples of finding area of regular polygons.